Hey, AP Chemistry, I'm going to try to go over all of your questions that you posted from both the FRQs and the multiple choice packet that I gave you last week. I wanted to make sure I went over a lot of any of your questions, but I also at the same time did not want to make a 3-hour video where I go over every single question. It just would take way too much time. So I've set up OBS here. I'm going to try to switch between my document camera and the Word documents because some of the questions from the multiple choice just are quick kind of theoretical questions, not a lot of calculations involved. And let's go ahead and start with the first question that people asked me about, which was number 5. And it says, in a laboratory experiment, a mixture of alkanes was separated into components by fractional distillation using the following apparatus. And we have this guy right here. This is a distillation setup. Distillation, at the very end of the day, all it is separating a mixture based upon the different components in the mixture's boiling point. So if you have 3 parts to the mixture, you're going to start heating up that mixture, and the things that boil first are going to go up here first and then get condensed out through this piece of glassware called a condenser. Basically how this works is there's water that goes through and it cools down the glass. So as the gas comes up here and then funnels down into the condenser, it cools down quickly and then it liquefies and then it gets collected down here. So it says the first fraction collected is fraction X, then fraction Y, then fraction Z. From this information we can deduce that A, B, C, and D. So what you see here is that X comes out first, then Y, then Z. Any option here that has anything to do with like molar mass or covalent bonds, it doesn't really have any effect because distillation is entirely based upon boiling point. The other way you could question that is like this is more volatile. So if something is more volatile, it means that it's more likely to be a gas. It escapes out of the liquid phase more quickly. So in other words, it has a lower boiling point. So the answers B and D immediately when I look at this are wrong because they have to do with molar mass and covalent bonds. So B and D, just throw those out. A and C are the only ones that could potentially make sense. A says fraction Y is more volatile than Z. C says fraction X has a higher boiling point than Y and Z. Fraction X has a higher boiling point. That can't be right because X came out first. And if X comes out first, it must have a lower boiling point because as the mixture was being heated up, it starts at a low temperature, then goes up. So fraction X would have a lower boiling point and then would get condensed down into the condenser and go into the beaker here, or flask. So the answer is A. Fraction Y is more volatile than Z. So that makes sense because Y would come out because it's going to be a gas more easily than Z is. And then our next question, question 10 here. It looks like a mathy question, so let me switch over to my document camera. Okay. So the question asks us, the levels of carbon dioxide in the air in a spacecraft can be controlled by passing the air through canisters containing lithium hydroxide in a laboratory trial. The air in a 5-liter container at 1.1 times 10 to the second kPa and 25 degrees Celsius was passed through a canister of LiOH. The pressure of the air in the container decreased to 100 kPa, measured again at 25 degrees Celsius. The mass of CO2 absorbed from the air sample by the LiOH in the canister was. So to answer this question, we need to figure out, well, how much carbon dioxide was actually absorbed by this LiOH canister. So I just kind of made a quick diagram here. The air going in has a pressure, this is 110 kilopascals, and it comes out as 100 kilopascals. So the carbon dioxide that reacts with the LiOH has a pressure of 0.1 times 10 to the second kPa, or 10 kPa. Now we want to know what mass of carbon dioxide was absorbed. So we're going to use PV equals nRT to figure this out because we could use that to figure out how many moles of carbon dioxide were absorbed by the LiOH, and then from there we can convert to grams. So I went ahead and did the math here. So 10 kPa, we're going to convert that to atmospheres. There's 101 kPas to 1 atmosphere, and so that gives us 0.0987 atmospheres. The number of moles of CO2, therefore, after plugging into PV equals nRT is 0.0202 moles of CO2. And then multiplied by the molar mass, it gets you 0.888 grams of CO2. After that, we had question number 15. Let me bring that up. So question 15 says, one possible reaction that occurs when trinitrotoluene, TNT, explodes is, and see that reaction equation there. When 1 mole of TNT explodes, the total volume of the gases produced from this reaction measured at 27 degrees Celsius and 100 kPa is closest to. So in this one, you're trying to figure out, okay, if 1 mole of the TNT explodes, how many moles of all of these gases will be produced, and then what volume will they take up at this temperature and this pressure? This is not that bad of a problem, but it's a little bit weirdly worded, I think. Let's go ahead and look at the math. So it's kind of a weird problem, but it's not that hard at all. So we have the reaction equation written out for you there again. We want to know how many moles of each of these gaseous products will be produced from 1 mole of TNT reacting. And so what would you do? You would go ahead and just do the molar ratio from TNT to each of these gaseous products. So what you would get is you would get 6 moles of carbon monoxide, 5.5 moles of H2 gas, and then 3.5 moles of N2. You get that many moles of each of those gases. And so therefore, the total number of moles of gas is 10 moles of gas. And then to figure out the volume, you would just put that into PV equals nRT, and then you can do the math. It's not too bad. It comes out to be about 240 liters, which is answer C. So around 240 liters is around C, 249. You're not looking for an exact calculation, something close to that though. All right, the next question is question number 16. A lot of people had a question about that as well. This one I'm not going to do any math with really, but this has to do with TLC, thin layer chromatography. This is something I did not get a chance to talk to you about in person. I went over this with a video. And remember that with TLC, it is a kind of chromatography where you have a piece of paper essentially, which will act as our stationary phase, and then a solvent, which will move through that paper, and then we have some kind of sample, which will be separated into individual components by the solvent that is being absorbed by the paper. And they tell us that we have, consider the following TLC plate of compounds X, Y, and Z developed using a suitable mobile phase on a polar stationary phase. So they're saying that the paper is made primarily with polar compounds, and the mobile phase, therefore, would be made with non-polar compounds. That's just your stationary phase and your mobile phase have to be opposing. One has to be polar, one has to be non-polar. And so we want to figure out what is the, let me see, maybe I do have some math here. Oh, I do have a picture. Let's go ahead and switch over to this. Okay. So our plate is polar, our solvent is non-polar. The stationary phase is the plate, the mobile phase is the solvent. And so what this is telling us is that more non-polar compounds will move with the non-polar mobile phase. Remember that like dissolves like. So since the solvent moving up the plate is non-polar, more non-polar compounds are going to move along with that solvent. And the question is, what is it again? The RF value of the most polar component in this TLC separation is, okay? So the most polar component of X, Y, and Z, the most polar compound is going to adhere to the polar stationary phase the most. In other words, it's not going to move along with the solvent very much. Non-polar compounds are going to move with the non-polar solvent. So this guy right here, the one that doesn't move very far, is the most polar because it's adhering to the plate. Its intermolecular forces are polar, And so the plate is polar, so they are attracted to one another, so it's not going to move along with the mobile phase. So to figure out the RF, the retention factor, we are going to calculate that based on the ratio of movement to the total solvent movement. The movement of this guy right here is 0.8. Come on. There we go. 0.8, I think it's in centimeters. It's not a big deal what it is. The total movement was 2.75, so the solvent moved 2.75 centimeters. And so the RF factor is going to be, we can put this in a calculator, 0.29. So RF factor is 0.29, and that is A. A is the correct answer. All right. The next question was number 18. Okay, number 18 says the graph shows the absorption spectra of 3 food dyes, blue number 1, red number 2, and yellow number 4. Which one of the following is the best wavelength to determine the concentration of red number 2 dye in a solution containing a mixture of all 3 dyes? So they give us the absorption spectrum, meaning they are on the x-axis here. They're measuring, okay, where is the best absorption of this compound? What wavelength is going to be best absorbed by this compound? So these peaks represent the best wavelength to have that compound be absorbed in terms of light. So the peak here for yellow number 4, the wavelength is approximately 425 or so. Number 2, red number 2, that's the one we're interested in. So the peak, the best wavelength is around 540 or so. So 500, 520, 540, about 540. So red number 2 is best absorbed by wavelengths of light at 540 nanometers. And so that's going to be C, 540. Blue number 1 is best absorbed by around 620 or so. But the peak here represents the wavelength that is the best to absorb that compound at. So 18, the answer is C, 540 nanometers. Next one, number 21 I have here. Okay, 21. To each of these 3 samples of a solution, a different acid-base indicator is acid. Thymol blue with a pKa 1 of 1.7, red to yellow. pKa 2, 8.9, yellow to blue. Methyl red, pKa of 5.0, red to yellow. And phenolphthalein, pKa of 9.6, colorless to red. The following colors are observed. So they tell us that we have some kind of solution, and we're adding in indicators to try to narrow down what the pH is. They tell us this about what they observe. So the thymol blue is turning yellow when they add the thymol blue to this compound. So that means that it's turning yellow, so that means that its pH is going to be greater than 1.7. Because remember that at the pKa of an indicator, either less than or greater than, the color is going to change. So since the thymol blue is yellow, we know for sure that it has a pH, the solution has a pH greater than 7, or 1.7, excuse me, 1.7. But we have a pK of 8.9 here, where it says yellow to blue. So thymol blue staying yellow means that the pH is between 1.7 and 8.9, somewhere in that range. Then they tell us that the methyl red is yellow, and the methyl red has a pKa of 5. So the pH has to be greater than 5 since the methyl red is yellow. They also tell us that the phenolphthalein is colorless. So the pKa of phenolphthalein is 9.6. So the pH has to be greater than 5, but less than 9.6. And also, it has to be less than 8.9 because the thymol blue did not turn blue. So the answer is going to be C. So since the thymol blue did not turn blue, our pH can't be above 8.9. And then the pKa of phenolphthalein, 9.6. We have a colorless solution, so the pH has to be less than 9.6. So the only option that makes sense here is 6.3 to 8.3. It's got to be greater than 5. It's got to be less than 8.9. So 6.3 to 8.3 is the best possible answer to this question. Could it be potentially somewhere a little bit more than 8.3? Yeah, but the best solution is going to be C, 6.3 to 8.3. Number 21, then number 34 is our next question. No, I have 31. So number 31 is the next question I have here. And it says, a desalination plant produces 200 gigaliters of fresh water each year. The maximum level of boron permitted in desalinated water is 0.5 parts per million, or 0.5 milligrams per liter. The maximum mass in kilograms of boron is permitted in 1 year's production of desalinated water this is a big old just dimensional analysis kind of question. So let me show this for you. So this is our limit for the amount of boron that can be in water. And what we want to do is we want to compare that, we want to get that value up to kilograms per gigaliter so that we can figure out what mass is allowed in the water. So 0.5 milligrams per liter, convert to grams, convert to kilograms, and then convert liters to gigaliters. There's a billion liters to a gigaliter. So this comes out to be 500 kilograms per gigaliter. And then this is how much water is outputted by the factory, 200 gigaliters. So our ratio of how much boron is allowed in the water is 500 kilograms per gigaliter. So we're going to convert to kilograms, just how many kilograms of boron are allowed in that 200 gigaliters, and that gives us 1 times 10 to the 5th kilograms of boron. That was number 31, and then I have number 34 as our next question. All right, consider the following reaction. IO3- plus 5I- plus 6H plus gives us 3 iodines and 3 waters. The correct half equation for the reduction reaction is, okay, this one, it seems weird, but it's really, really easy. Because you're looking for a reaction in which electrons are being added, since it's a reduction reaction. So immediately A and C can be thrown out because that would be oxidation where electrons are being removed. So A and C just get thrown out immediately. And then B and D. B is not right. Why is it not right? Because this part right here, the H plus being turned into water, that's not a part of the original redox reaction. So this is our balanced redox reaction, and of course redox reactions have H plus and H2O. So as balancers. So the balancers are not going to be used to do the redox reaction. Another way you can tell really fast here is that if you look at the 5I- to I2, remember that I- has to have an oxidation number of -1, and then I2, remember the diatomics always have an oxidation number of 0. So iodine became oxidized, and then IO3-, this is going to be IO3- where you're going to have oxygen in -2, so it's a -6 in total, and then iodine is going to be a +5. So this iodine here is becoming 0 when we go over to the I2. So therefore, the IO3 is the one that's being reduced. It's being reduced. H plus over here, H plus is +1, and then over here in water, it's still +1 because oxygen is -2, and then there's 2 hydrogens, so they'd have to be +2. So IO3-, that iodine is the one that's being reduced. You can You can do just a quick ABC. It's got to be process elimination, or you can go ahead and do the oxidation numbers thing. Really, you're always trying to go faster on the AP test, quicker based on just basic instincts of chemistry. C's got to be the right one because it's a reduction reaction, and then you can't use the H pluses. So, excuse me, yeah. Or D is the right answer. D is the right answer. That's the reduction reaction. The reduction reaction. So IO3 minus is being reduced. Can't be B because it's a H plus is a balancer. So you can also do the oxidation number thing, but overall it's got to be D. All right, number 39 is the next one I have. Let's see what this is. The densities of ethylene glycol, water, and wood alcohol are 1.1 grams per milliliter, 1 gram per milliliter, and 0.79 grams per mil, respectively. Suppose an object floats in water and the ethylene glycol in water and ethylene glycol, but sinks when placed in wood alcohol. Which would be the density of the object? So we're looking essentially for a density that is lower than 1.1 and 1, but greater than 0.79. So that's got to be D. Remember that things float when they have a density less than the thing that they're in. Next question, number 52 is what I have here. This one. So it says toluene is a gas additive used to improve octane rating. If 22 milliliters of toluene, which has a density of 0.867 grams per mil, are burned in excess oxygen, how many water molecules are produced in the process? Let me go ahead and switch over to the document camera. So the reaction that takes place in combustion, you should have this memorized, is this guy right here. So reacts with oxygen to produce water and carbon dioxide. This is how you would balance it. And we want to figure out, well, how many molecules of water would be generated from the combustion of 22 milliliters of toluene, which has a density of 0.867 grams per mil. So this is, again, kind of just a basic dimensional analysis problem. 22 mils converted to grams using the density, and then converted to moles, using the molar mass of toluene, and then converting to moles of water by using the molar ratio, 4:1, and then multiplied by the Avogadro's number to get molecules. And you should get around 5 times 10 to the 23rd molecules of water. Next question is number 58 that I have here. And this is actually a topic I did not get a chance to go over with you guys, and I kind of just forgot about it. It's not a very common problem to see on the AP test, but it might show up. It says this: the bond order of the nitrogen-oxygen bond in the nitrate ion NO3- is about, and you gotta draw the picture first of all. So draw nitrate first. So the nitrate has a double bond from the nitrogen to one of the oxygens, and then single bonds to the other oxygen atoms. Now, bond order is this. It is equal to the number of single bonds, and that's a weird term to use, but the number of single bonds divided by the number of bonding groups. So I've circled this in purple. How many single bonds are in the Lewis dot structure for nitrate? 1, 2, 3, 4. I know that double bond is, you don't say it's 2 single bonds, but for purposes of bonding order, yes. So there are 4 single bonds present in the nitrate ion. And then we're going to divide by the number of bonding groups. And there are 1, 2, 3 bonding groups in the nitrate ion. So this is 4/3, which is about 1 1/3. So the answer is 1 1/3. Number 60 was also asked about. I'm going to tell you this. Don't worry about it. That has that compound, IF3, has 5 spots for bonding, so it comes out to be sp3d2 hybridized, I believe. That is never going to be on the AP test. All you have to worry about with hybridized orbitals is sp3, 2, and 1. So don't worry about number 60. After number 60, we had number 67 as a question. Let me bring it up on the screen first. So it says, what is the equilibrium concentration of F2 at 100 degrees Celsius if the initial concentration of HF is 0.25 molar and the equilibrium constant is 2.7 times 10 to the negative third. And then they give us the reaction equation. So in this problem, we are going to try to figure out the concentration of F2 from the initial concentration of HF. This is a basic ice problem from equilibrium days many moons ago. They give us the equilibrium constant. They give us the initial concentration of HF. We want to figure out what is the value, the concentration of F2 at equilibrium. So set up your ice table like so. So you're going to lose X of HF to make H2 and F2. You're going to get X of each of these. And then set up your equilibrium expression. The equilibrium constant is equal to products over reactants. And that's going to be X squared on top because it's X times X. And then 0.25 minus X, all of that squared. Why is all of that squared? Because of this guy right here, we got a molar coefficient of 2. Remember that molar coefficient goes as an exponent in the equilibrium expression. Remember our little rule that if the equilibrium constant is really, really small, that means that our change, our X value, is going to be really, really small as well. So we can kind of exclude it from the calculation, making the calculation much easier. And so just solve for X. I made a little boo-boo somewhere along the way, but I fixed it. You'll get a value of 1.3 times 10 to the negative second molar. That would be the value, the concentration of F2 at the end there. So this is just a basic ice problem. The big hang-up always is people forget about that too. Next one. The last question people had was number 71. The Gibbs free energy change at 298 Kelvin for the reaction SO2 reacting with O2 makes SO3 is negative 141.6 kilojoules. The equilibrium constant for the reaction is written as, we just have to figure out the equilibrium constant. This one's not too bad. This is just a simple number crunch. So remember that the equilibrium constant is also a part of the Gibbs free energy, and delta G is equal to minus RT L times ln K. So if we want to solve for the value of the equilibrium constant, that would be K equals Euler's number raised to negative delta G over RT, Boltzmann's constant there. And so just plug in the numbers, and we get 1.51 times 10 to the negative 25th. One thing to point out here, this is all in kilojoules, so Boltzmann constant should be in kilojoules per mole Kelvin instead of just joules per mole Kelvin, so 0.008314. And so that comes out to be about 2 times 10 to the negative 25th as an equilibrium constant. So that's the answer on the ABCD question. It comes out to be 1.5. You just do the normal calc, but the option of 2 is there on the multiple choice. All right, and then people asked about number 3 primarily from the longer questions that I gave. I'm not too surprised because this is one where a lot of students make a mistake about the titration curve stuff. Don't feel bad. I like this problem, though. It's a good problem. Don't be surprised you see something like this on May 14th. However, feel like acids and bases are not going to be on the test. I think I wrote that too. I'm going to double check that later. Might have changed. I don't know. We'll see. Anyway, number 3 says we have 30 mils of 0.75 aniline, which is C6H5NH2, and it has a base constant of 3.8 times 10 to the negative 10th. And it's titrated with 0.5 molar HCl. And we're asked to find the initial pH, the pH at the halfway point, the pH at the equivalence point, the pH 160 mils of 0.5 molar HCl have been added. So this is a big question, big question. All right, so a lot of different parts here. This uses a lot of different things from everything we've learned about. The first part is to find just the initial pH of the aniline. That's not too bad because it's just an ice problem. So set up your equilibrium for the reaction of the base with water. Remember, this is a base. Aniline is going to accept a proton. So with water, it's going to make the conjugate acid, and OH minus. It has an initial concentration of 0.75 molar. You're going to lose X of it. You're going to gain X of our conjugate acid and hydroxide. So our equilibrium expression is going to be the value of Kb equal to X squared, X times X, over 0.75 minus x. Again, assume, since the equilibrium constant is very, very small, the value of x is really, really small, so we can ignore it in the denominator here. So just solve for x, do the math there, you get a value of 1.69 times 10 to the negative fifth. That is the concentration of hydroxide. So to find the concentration of, or to find the pH, we're going to figure out the pOH of the solution, plug it into negative log of the OH minus concentration, get 4.77. Remember that the pH plus the pOH is equal to 14, so 14 minus the pOH is equal to the pH, which is 9.23. So the pH of the initial pH of the solution is 9.23. The next question is, what is the half equivalence point? The half equivalence point of any solution is equal to the pH. The half equivalence is always equal to the pKa of that solution. So we need to find the pKa of aniline. Well, remember that the pKb plus the pKa of a solution is equal to 14. Okay, we were given the Kb of the solution, so we can figure out what the pKb is, which is 9.42. And so the pKa is 4.58. So the pH at the half equivalence point of this solution is 4.58. Some of you are probably thinking, that doesn't make a lot of sense, it's a base. Well, remember that a weak base reacting with a strong acid is ultimately going to have an equivalence point which is lower than 7. And so in this case, it just kind of works out that the half equivalence point is really, really far off from the initial pH. The addition of hydrochloric acid is going to decrease the pH really, really rapidly. And the halfway point is going to be about 4.6. The equivalence point, as we're going to see in just a second here, is going to be quite a bit lower. So to find the pH at the equivalence point, we're going to need to figure out how many moles of acid actually reacted with the base. Now, remember that the equivalence point is when the number of moles of acid equals the number of moles of base. We can figure out how many moles of base there are by multiplying the concentration of the base, aniline, by 0.03 liters, which is the volume that we have. So there are 0.0225 moles of aniline in the solution. Therefore, we're going to add 0.0225 moles of acid in order to reach the equivalence point. Something to keep in mind too, well, what volume of acid did we add? We'll use this number later. The volume of acid that we added is going to be 0.045 liters to get to that equivalence point. Now, at the equivalence point for the reaction between a weak base and a strong acid, the conjugate acid of that base is going to continue to react with water and therefore lower the pH below the equivalence point. So you got to remember that for aniline, its conjugate acid is going to lower the pH more. So we want to figure out, well, how much of the conjugate acid have we made from this reaction, and therefore we'll react with water to lower the pH even more. That's how we figure out what the pH is. So at equivalence, we are going to have the reaction of the aniline compound, the base, with H plus from the HCl. And this is just a BCA table. Everything is a one-to-one reaction. We have, at equivalence, 0.0225 moles of each of them. We have 0 of our conjugate acid. We use up all of the acid and all of the base, and we produce a one-to-one ratio of 0.0225 moles of the conjugate acid. Okay, cool. Now, what is the concentration of that conjugate acid in our solution? Well, that's going to be the 0.0225 moles divided by how much acid we added, plus the amount of the volume of the base that we started with, which is 0.03 liters. So 0.045 plus 0.03 liters is 0.075. So the concentration of the conjugate acid is 0.3 molar. That's its concentration at equivalence. So therefore, we're going to move on to a new equilibrium reaction between the conjugate acid and water to figure out how much H3O plus is produced by the conjugate acid reacting with water. So we start at 0.3. We have no more of that aniline present. We have no H3O plus present. Well, we do technically, but it's not involved in this reaction right now. So minus X of the conjugate acid plus X of each of our products. So do our basic equilibrium setup here. The Ka, we have to figure that out. So we knew the pKa from a previous problem, so it's 10 to the negative 4.58. The Ka is 2.63 times 10 to the fifth. Remember the Kb and Ka. The Ka is going to be for it's the conjugate acid here, so we're going to use the Kb to do that. But we figured out the Ka earlier. So the Ka of the conjugate acid is 2.63 times 10 to the negative fifth, and that's going to be equal to x squared over 0.3. Why over just 0.3? Remember, the conjugate acid's equilibrium constant is really, really small, so that value of x is really, really tiny. Okay, so x is equal to 0.00281. That is equal to H3O plus's concentration. And then plug that into negative log times H3O plus, get a value of 2.55. So the equivalence point is actually at 2.55. Seems kind of crazy, but the math works out for this one. Next question. After 60 mils of 0.5 molar HCl is added, HCl is I'm not even reading the question right. What did it say? Yes. So it says, what is the pH once 60 mils of the HCl is added? So with this question, it's saying, okay, we went way past the equivalence point. We added way more HCl than we should have. What's the pH going to be? So we originally added 45 mils of HCl. We're adding another 15. At this point, we've added way more HCl than necessary. So the effect of the conjugate acid reacting with water and all that stuff, who cares? That weak acid is not going to affect the pH significantly. The presence of HCl, a strong acid, is going to way affect the pH more than anything else could, whether it's a strong acid or a strong base. So we need to figure out, well, how many moles of HCl more have we added? And then from there, we can figure out what the pH is. So we added 60 mils of HCl at a concentration of 0.5 molar. We therefore added a total of 0.03 moles of HCl. How many moles of HCl did we use to neutralize this solution and get to the equivalence point? We figured that out earlier, 0.0225 moles. So we have an excess of 0.075 moles of HCl. That's all in excess. So we can figure out the concentration of H3O plus because we know how many moles of H3O plus are going to be there in excess, and we can divide by the new volume. So we start with 0.03 liters of the aniline. We added 0.06 liters of the base, or the HCl. So the concentration of H3O plus is now going to be 0.0833 molar. And so we know that's H3O plus's concentration. So we plug that into our pH calculation, 1.08. So adding 60 mils gets us to 1.08. The next question. Pull it up here. Of the below indicators, which would be the most suitable for the above titration? Explain. So remember that for any solution, the indicator that we want to use is going to have a pKa close to the pH at which equivalence occurs, so that when we switch from one side of the curve to the other side of the curve, the indicator is going to change colors close to that pH equivalence point. So we need to figure out which of these compounds has a pKa close to 2.55, the equivalence point. And so what you'd want to do is when you look through all these Kas here and calculate which of them has a pKa close-ish to 2.55. It doesn't have to be perfect. It's just asking which is the most suitable. So the correct answer is methyl yellow, because if you take this value and then figure out the pKa there is 3.1. This methyl red would be 5, and then all the rest have numbers which are much larger for pKa. So methyl yellow has the closest to 2.55 at 3.1. It's not the best in the world, but it's close enough, and that's the most suitable of the available indicators. So you just want to take our Kas, to turn into pKa by doing the negative log of it, and then figure out which of them is closest to 2.55. Next question. Zoom down a little bit. It says, when preparing a buffer solution of aniline, what mass of conjugate acid must be added to have it buffer at a pH of 5.0? Assume the change in volume upon adding solid conjugate acid to prepare the buffer is negligible. Okay, let me switch over to my document camera. So to make a buffer, remember, to make a buffer you have to add the acid and its conjugate base, or in this case, since we have a base, we're going to add its conjugate acid to the solution. We're assuming that our conjugate acid is some kind of solid, like a sodium analyte. I don't know what it'd be called. So we're going to add our conjugate acid to the base to figure out, to make a buffer. So we want to know how much of our conjugate acid do we need to make. To answer the question, the best way to do it is the Henderson-Hasselbalch equation. Remember that the Henderson-Hasselbalch equation for a base is going to be the POH is equal to the pKb plus the log of this expression right here, the conjugate acid's concentration divided by the base's concentration. So if we wanted to have the solution buffered at a pH of 5, that would mean the POH would be 9. So I'm thinking this in terms of bases because our solution is a base. You could switch all up and do it with the other version of the solution, of the Henderson-Hasselbalch equation with acid, but I feel like it's a little bit easier to do this with the base version because we're working with a base primarily. Anyway, 9 for the POH is going to be equal to the pKb of aniline, which we calculated earlier is 9.42, plus the log of the concentration of our conjugate acid divided by the concentration of the base, which we knew earlier was given to us as 0.75. And so from here, what I'm going to do is do a bunch of math, essentially. I'm going to do a bunch of math to figure out the concentration that the conjugate acid needs to be. Also, it's a 330 milliliter solution, so the concentration is going to be, or the number of moles, so I'm going to take concentration, get it into moles, and then from there get it into grams. So concentration multiplied by 0.03 liters gives us this many moles of the conjugate acid, and then convert from moles to the conjugate acid in grams, and we get 0.804 grams of our conjugate acid. Okay, I think I'm actually going to pause right here. I'll make another video with the FRQs in just a little bit. This has already been a really long video. This is just the multiple choice section and the a short answer number 3, which kind of turned into a huge answer in my opinion, but it is what it is. Watch this. Hopefully this has helped a lot. I'll get the FRQs done soon, hopefully. We're working on it. Have a great day, guys. Bye.